Let us analyze tweets using Python NLP techniques. So here we will take various tweets and we will analyze what is the sentiment of these tweets and how we can use it for performing various advanced NLP techniques also, like LSTM and GRU. So initially we have the tweets here. Now the tweets.csv file includes the ID, the label, and the tweets as such. Now here 0 refers to positive sentiment and 1 is negative sentiment. So let us map it correctly, where let 1 represent negative, positive, and 0 represent negative. So we map all zeros to ones and ones to 0. So we have 7920 records, 7920 labels, and 7920 tweets. So let us first of all understand if there are missing values. There are no missing values. We drop ID, which is because it is not required. So there are positive sentiments 5894 records and 2026 with negative sentiments, and that is nearly 75% is 1 and 25% is negative reviews. Plotting the same using Seaborn, and then we are going to do data cleaning. Now for data cleaning, we randomly take some tweet and just check what is the cleaning that is required in such kind of tweets. So there is, we see some URLs, we see hashtags, and we see the at quoting. So so here on this particular tweet, we try to remove apostrophe s to is. We change that. So now as you can see, it's time becomes it is time. So making use of various short forms is also needed. So just randomly checking on any other tweet. Not heavy machinery, but it does what I need to do. Apple really dropped the ball with that design. And then we can remove the usernames. So whatever is at, that can be removed. That is, we are just checking to do it for initially for one tweet. The hashtags can be removed. Only the hash can be removed. We can also remove the hyperlink. So here, if you see the first review, here there was, in the first review, there was a hyperlink which is removed here. See here, there was a hyperlink which is removed. So this, we are initially trying it only for particular tweets. We'll apply the same for all the tweets that are there. We can retain only the alphabets, get rid of punctuation, special characters, and digits. So anything else can be just replaced by a space. So we have an LTK. And we also get the stop words from English language. We also get the stop words from sklearn package, which has more number of stop words when compared to NLTK. So we get 378, nearly 378 stop words, and then text normalization can be done using stemming, porter stemming or lemmatization. Stemming will just stem the suffix of the word without leaving the word in its root form, in its meaningful form, whereas lemmatization will always leave the word in its meaningful format. Contractions are also to be checked. So we using which contraction library will help me. So like for example, if I say I pass, I'm bored, it will give me the correct I'm bored expansion of it. So instead of we manually doing it is time, we can just make use of this contractions class. And now we are with everything that we have just given, we are going to specify the function. Like initially contractions will be fixed, and then it will remove the user mentions, it will remove hashtags, remove any kind of hyperlinks, and also it will remove any punctuation, special characters and digits. It will also make it into a lowercase, and it will check that the length of the token has to be more than 2. It should not be a single word that is there, and it will also perform lemmatization on all the words. So once we apply this tweet cleaner function for this particular tweet, we will get like this: time for new wallpaper, phone wallpaper, wall screens, Galaxy, Samsung app. So this we apply for all the tweets that are there. And we can also check for all the words. We are now creating list of all the words that are there from these tweets. So there are 400 unique words that are used in this particular, in all these tweets. So checking on the 50 most common words from these tweets, it is iPhone. iPhone is really trending, is what we see here. My, to, I, the. Apple is again Samsung, iPhone, Apple, phone, Sony, iPhone. So as we can see, these are the words which were really in trend from the tweets that were captured at that time. And then there is the frequency distribution. Also iPhone has been used 2077 times and so on. We can also do a frequency distribution plot for cleaned tweets. Now in the clean tweets we see iPhone, Apple, the Samsung, and now for the clean tweets, these are what is used. And we have various combined stop words also. Now if we try to remove the stop words from these tweets and then look at the top 25 common words, it is iPhone, Apple, Samsung, new, phone, Sony, follow, pick, like, iPad, love, day, life, Android. So now you know it is mostly the topics around phones and iPads, and it's a very photo of the day, finally, update, good, amazing. So these are the various words that were commonly used. We can also create a word cloud for the same. So we took some random text and then just showing the sample code of how to create a word text. So for this particular sample text that is there, that is the latest retail inflation data and so on. Now here inflation is one commonly used words, then there is price, then there is food, years. These are other commonly used words. And now what we are going to do is, whatever are the clean data set, we are going to store it in all the tweets. I'm storing it in cleaned tweets v1.pickle, and this will be further used for our next set of analysis, where we are going to do sentiment analysis using bag of words T and TF-IDF model. So initially loading all the libraries and getting all the cleaned tweets. So we have 7920 tweets with 4 columns. 4 columns as in the label, tweet, clean tweets, and the clean tweets without stop words. Positive and the negative tweets and the commonly used words as we already saw. This is the word cloud for all our positive words, positive vocabulary. And for all the negative vocabulary, we can see that also we can create a bag of words model. Word cloud model. Now we are going to make use of bag of words. So a bag of words, TF-IDF and Ngram will be used for, and basic language model will be created using this. Then we, in the next part 3, we are going to make use of word-to-vec, glove and fast text. That is the distributed language model. And then finally we are going to check on the large language model, the LLMs, for which we will make use of transformers. So here we have the cleaned tweets and the label, and now first of all we apply train test split and then applying count vectorizer. So initially we apply count vectorizer for X train and then applying the same object for X test. Here we are getting 13481 words. So we have total of 13481 words, 6336 records in the trained data set, applying the logistic regression model on this, and we are getting an accuracy, the training accuracy of 97% and a test accuracy of 87%. TF-IDF model, well, that is instead of count vectorizer, instead of bag of words, if I use TF-IDF, fit transform on X train and the transform alone on X test, because I would not want my X train parameters to be reflected in the X train X test. That will lead to data leakage. That is, if I do it on the entire data set, then the test set gets information about the train set. So here applying TF-IDF, I get TF-IDF and logistic regression. We get 91% train accuracy and 87% as the test accuracy. So if we use class weight equal to balanced and penalty equal to L2, that is the regularization, if we apply, then it slightly improves, accuracy slightly improves to 92.6. And we also specify the regularization parameter C equal to 2, improving the accuracy further to 94. Specifying solver equal to liblinear, that did not help, the accuracy came to 92.4. and so we have tried various methods here. Now coming to the next one, where we are going to make use of word-to-vec and the embeddings. Again making use of the same clean tweets. So we split the data into X train, X test, Y train and Y test. We clean our tweets and we apply splitting on the words. So here we make use of the words that are there. So as you can see, some random words has gone to X test. 2221, 379, 4823, some random indexes have gone to this. So now we are going to make use of word-to-vec architecture, where we are going to apply CBA on continuous bag of words and skip gram. So we make use of the GenSim class for this. Get the word to vec model. So here we're going to use a vector size of 300, and here we have word to vec vocabulary model, which is 13262. That is, there are total of 13262, 13,262 words. Each word is going to be represented as a vector of 300 dimensions. Okay, each word, like for example, if I take king, it is going to be a vector of 300 size. Now, so that is going to give me 397860. This is going to be my total size of the dimension that is there. So here X train is 6336, two columns. Each vector size is 300, and there are total of 6336 words, and these are the various words that are there. So now we write a function get document vector, using which we pass the model and the document, and then here we check if that token appears. Then we calculate the mean of those tokens. Otherwise, we embed the model with zeros. So this word to vec document embedding, see, this we get, that is the mean of all the terms that is there. Otherwise, it gets embedded with 0. So along with the tweets, we also have now the word to vec document embedding, word to vector document embedding, and this we are getting from this particular function, which tells that takes the mean of all the tokens that is there. Otherwise, if it is not existing, if that word itself is not there in the dictionary, like for example, we have some arg, some words, some random words which are there, like something like ATB, not ATB, but then like, ABT, or any words which does not make any sense, that has to be embedded with 0. Applying the same on the test set also here. And now we apply the random forest method, and once we apply the random forest method, we are getting an accuracy of 80%. So here word to vec embedding is used, word to vector embedding is used, and then random forest is applied. The next is again making use of the same pickle. So for working on the cleaned tweets, we make use of LSTM, GRU, bidirectional, dense, dropout, embedding, path sequences, sequential, model, one hot. Okay, we make use of all these libraries. So the vocabulary size is 1000. We apply Porter stemmer, and then we get the reviews. Now here these are the indexes of the various reviews. and these are the various reviews after porter stemmer is applied. Now one hot encoding will perform one hot method will apply one hot encoding on these words, and then we finally get the representation of these words like this. So we have 7920 Y columns, and if we just take the first column, it has the representation of the words. Splitting the data for train test split into 80 and 20, and then now we are going to build an LSTM model. So LSTM is an RNN architecture which is used in deep learning, and here RNN is a deep learning model. See, CNN is mostly used for image tasks, but RNN is mostly used for NLP tasks. So till now what we have seen is machine learning work. Machine learning, it will include random forest, logistic regression, XGBoost, as we also. The next step further is applying deep learning to these models. So under deep learning, the first thing is RNN. Now RNN comes in two forms. One is LSTM and the other one is GRU. LSTM helps to capture the long-term dependencies. So they see in any kind of conversation, like let's say if I'm building a chatbot, it becomes very important to remember the context of what we have earlier spoken. So that is what RNN is, that there is an input gate, there is a forget gate, and then there is an output gate. So in the input gate, I pass the information. In the forget gate, it decides what is the information that has to be retained and what is the information that has to be forgotten. So depending upon that, there is some information that still goes out, it gets retained, and there is some information that is forgotten. So so like that, there is few things which are always remembered. Like let's say if I have a long story, then there are few things that I would want to remember from the story to take it further. There are few details which I would want to forget. So something like that only. There is an input, like an input sentence coming every time. What are the details that can be forgotten and what are the details which hold importance? This is what LSTM helps us to do. Now LSTM has a lot longer process. The shorter process was GRU. From GRU, what we move on further is, we can also have bidirectional RNN. So either bidirectional LSTM or bidirectional GRU, that is also possible, where it's possible for communication in both the directions. That is, like for example, it can help me to process the input from left to right also, and also from right to left the input can be processed. The next thing that came up is LLMs. Now LLMs are available, that is LLMs have evolved over years in 5 stages. So initially there was encoder decoder. I will list down the stages here. Stages of LLM. So LLMs have evolved as encoder and decoder initially, and then it was attention process was developed, and then after that came in transformers, and then came in transfer learning, and then finally what evolved is LLM, which is the term that we frequently hear today. So encoder decoder is a simple sequence to sequence architecture, and it is suitable for small sentences. Now what happens in the next one is attention. In attention, all intermediate states are also available. All intermediate states as in as I was mentioned, that there are certain things that are forgotten. So here all intermediate states are also available under attention. The next is transformers. Now the transformers here, the whole idea was parallel processing. So a lot of parallel processing gets done with the help of transformers. And so now these transformers, they needed hardware, they needed time and a lot of data. So what helped here is transfer learning. Now transfer learning happens in two stages. One can be pre-training, that is I pre-train a model and then I fine-tune the model to use it for my purpose. So but then this particular concept of transfer learning was not used for NLP initially, because one is task specificity. So all NLP tasks are different. So it's not like, so like sentiment analysis is different, then text categorization is different, text clustering is different. So all these are different. And there was not lack of data also. So here language modeling was used for pre-training. So language modeling was used, and that's how this LLM developed. So LLM is nothing but a combination of transformers, that is a lot of parallel processing, along with transfer learning, that is I pre-train the model and then I fine-tune the model for my own purpose. And using these LLMs only, I have got various advanced models like BERT, GPT. So these models are got. So this was an introduction to how deep learning in NLP has evolved over years, taking us finally to LLMs 2 is what we're seeing now. So here I develop a deep learning model where I include embedding and then LSTM, 100 layers, and then drop out at 40%, a dense layer of 1 finally to get the output. So this is a sequential model which initially includes an embedding, LSTM of 100 nodes, drop out at 40%, and then finally the output layer. So working on this, I get an accuracy of 95% accuracy. Similarly, applying, instead of LSTM, if I apply GRU and everything stands same, then I'm getting a final accuracy of 95%. Bidirectional LSTM and GRU can also be used. So this is bidirectional GRU, processing the data in both the directions, and that has given the accuracy of 95. This is bidirectional LSTM, and accuracy is 91. Transformer models can also be used, which I will. So initially I load the needed packages. I make use of the text classification model here. So applying this particular model for the tweets, like for example, let's say this tweet, which is secure study show malware PC come PDF exploit Apple user. It shows that it is a negative tweet, 0.99 being the score. If I take the 0th tweet, which is fingerprint pregnancy test, Android apps beautiful cute health, IGERS iPhone only, iPhone. So this shows that it is a positive sentiment with 0.98. So I can pass any review to this, and see, this is a movie review, and this shows that it is a positive review. And so like this I can make use of my model to understand of this is using the transformers model. See here I got that object using classification. Okay, so now I got that model, and applying that model on various reviews that we have, this is what we are getting. So these transformers will have certain models already. I'm loading that model. The link to all these notebooks will be given.